Differentiation from first principles. When it comes to calculating the derivative dy dx, we prefer to use the definition dy dx equals the limit of f of x plus h minus f of x over h as h approaches 0, rather than dy dx equals the limit of delta y over delta x as delta x approaches 0. So this is the formula for differentiation from first principles, and you should learn this off by heart. It's not in the formula book. So we use this formula rather than delta y over delta x because the first expression avoids the use of increments, delta y and delta x, also called infinitesimals, which caused serious problems for many early mathematicians. Calculating the derivative by using the limit definition is called differentiating from first principles. Although many functions can be differentiated from first principles, on our course we are only required to be able to differentiate linear and quadratic functions from first principles. Differentiation from first principles of linear functions. A linear function is one of the form f of x maps to ax plus b, where a and b are real constants. Example 1 shows how we can differentiate such functions from first principles. The function f is defined by f of x maps to 5 minus 3x. Part 1. Differentiate f with respect to x from first principles. So we're going to let y equal f of x, which is equal to 5 minus 3x. Then dy dx will be equal to f prime x, which is the limit of f of x plus h minus f of x over h as h approaches 0. So we're going to swap f of x plus h for 5 minus 3 times x plus h. So basically we took our function f of x and we wrote it down, but we substituted in place of this x plus h with brackets around it. Next we bring down the minus, and then we swap f of x for 5 minus 3x, which is our function given. And this is all divided by h. Next we're going to multiply out our brackets. So we bring down the 5, minus 3 by x is minus 3x, minus 3 by h is minus 3h. Then we bring down the minus and the 5 minus 3x in brackets. And again, that's all divided by h. At this point, you can multiply in the minus into the brackets. So minus by 5 is minus 5, and minus by minus 3x is positive 3x. Or you can just start to cancel out straight away. So 5 minus 5 will cancel, and minus 3x minus 3x is plus 3x, so they'll cancel. So you're left with minus 3h over h. So we have the limit of minus 3h over h as h approaches 0. We can now cancel out the h's, because there's one on the top and one on the bottom, and we're left with minus 3. So the derivative of f of x, which is equal to 5 minus 3x, is minus 3. Part 2. Explain why the instantaneous rate of change of f of x for any value of x is the same as the average rate of change of f of x over any interval. The derivative dy dx equals f prime x gives the instantaneous rate of change of y equals f of x. In this case, dy dx is equal to minus 3, a constant. Hence, the instantaneous rate of change of all points on the curve is minus 3, i.e., for each 1 unit increase in x, y decreases by 3 units. The average rate of change is the slope of the line joining 2 points on the curve. But because in this case the curve is the line y equals 5 minus 3x, the average rate of change will just be its slope, so i.e. minus 3. Hence, the instantaneous rate of change and the average rate of change are the same for a linear function. So this is important. The instantaneous rate of change and the average rate of change are the same for a linear function. Differentiation from first principles of quadratic functions. A quadratic function is one in the form f of x maps to ax squared plus bx plus c, where a, b, and c are real constants. Example 2 shows how we can differentiate such functions from first principles. The function f is given by f of x maps to 2x squared minus 3x plus 5. Part 1. Differentiate f with respect to x from first principles. So we let y equal f of x, which is equal to 2x squared minus 3x plus 5. Then dy dx is equal to f prime x, which is equal to the limit of f of x plus h minus f of x over h as h approaches 0. So we're going to take our function 2x squared minus 3x plus 5, and we're going to add h to each of the x's. So we end up with 2 times x plus h squared minus 3 times x plus h plus 5. So we took our function and we took each of the x values and we added a h with brackets around it. Next we bring down the minus and the f of x function, which is just 2x squared minus 3x plus 5. And make sure you've got brackets around it because you're going to multiply in the minus. And then that's all divided by h. So next we're going to multiply out our brackets. So 2 times x plus h squared. So we work out the x plus h squared first and then multiply in the 2. And we get 2x squared plus 4xh plus 2h squared. Then minus 3 by x is minus 3x, minus 3 by h is minus 3h, and we bring down the plus 5. Then we have our minus, and then we have 2x squared minus 3x plus 5 with brackets around it. So again, at this point, if you want, you can multiply the minus into the brackets, or you can just start to simplify. So 2x squared and minus 2x squared will cancel. Minus 3x and minus 3x, which is plus 3x, will cancel. And plus 5 and minus 5 will cancel. So we're left with 4xh plus 2h squared minus 3h, all divided by 5. Now at this point we can factorize out the h. So we have h times 4x plus 2h minus 3. This h will cancel with this h, but not the one inside the bracket. So we're left with the limit of 4x plus 2h minus 3 as h approaches 0. There's no h stuck onto the 4x, so we bring it down. 2 times h becomes 2 times 0, so that just cancels out. And the minus 3 we just bring down. So the derivative of the function 2x squared minus 3x plus 5 is 4x minus 3. And you should always check your answer using our differentiation formula from our formula book, or just our method of differentiation. So for 2x squared, to differentiate this, we bring the power down in front and reduce the power by 1. So 2 comes down in front, 2 times 2 is 4. We reduce the power by 1, x squared becomes x to the power 1, which is just x. And then for minus 3x, we can just cancel off the x, so we're left with minus 3. And plus 5 is a constant, so we cannot differentiate it with respect to x, so we just cancel the 5 as well. So we're left with 4x minus 3. Part 2. Give an interpretation of the derivative in terms of the curve. The derivative dy dx is equal to f prime x is equal to 4x minus 3 is an expression, or a function, derived from the given function y equals f of x, which is equal to 2x squared minus 3x plus 5. It gives the slope of the tangent to the curve at any point on the curve, and hence is sometimes called the slope function. It may also be interpreted as an expression for the instantaneous rate of change at each point on the curve. So when you think of the word instantaneous, think of the word instant. So it's the rate of change at each instant on the curve, or at each point. Part 3. Find the instantaneous rate of change of f at x is equal to 2, i.e. find f prime 2. So we worked out that f prime x is equal to 4x minus 3. We worked that out in part 1. So to calculate the instantaneous rate of change at x is equal to 2, we substitute 2 for x in the expression for f prime x, i.e. we calculate f prime 2. So the instantaneous rate of change when x is equal to 2 is equal to f prime 2. So instead of 4x minus 3, we have 4 times 2 minus 3, which is 8 minus 3, which is 5. So the instantaneous rate of change when x is equal to 2 is 5. Part 4. Find the average rate of change of f over the interval from x is equal to 2 to x is equal to 3. So f of 2 is going to be 2 times 2 squared minus 3 times 2 plus 5, which is 7. So what we did was we substituted 2 into our original function f. And f of 3 is going to be 2 times 3 squared minus 3 times 3 plus 5, which is 14. Thus, the average rate of change of f over the interval from 2 to 3 is delta y over delta x, which is the change in y over the change in x, which is 14 minus 7, so the change in y, over 3 minus 2, the change in x, which is 7. It is important to realize that differentiation, i.e. obtaining the derivative, is not always possible. It can be shown that for a function f of x to be differentiable at x is equal to a, it is necessary for the function to be continuous at x equal to a. This means that f of a must be defined, as must the limit f of x as x approaches a, and the limit of f of x as x approaches a must be equal to f of a. But this is not enough. For f of x to be differentiable at x equal to a, it is necessary for the left derivative, so f prime x minus, or negative, to be equal to the limit of f of x plus h minus f of x over h, as h approaches 0 from the left, and the right derivative, so f prime x positive, which is equal to the limit of f of x plus h minus f of x over h, as h approaches 0 from the right, to be both defined and equal. So in order for f of x to be differentiable at x is equal to a, the left derivative and the right derivative, they must both be defined and they must be equal to each other. So for recap on how limits are defined and equal, left limits, right limits, and so on, you can have a look back at the previous few videos. One example of a familiar function that is not differentiable at a point is f of x maps to the modulus of x, which is not differentiable at x is equal to 0. So here we have our x-axis and our y-axis, and here we have the graph of y equals the modulus of x, and this graph is not differentiable at x is equal to 0, so the apex of our graph. This function may also be written f of x maps to x if x is greater or equal to 0, and minus x if x is less than 0. And the curve y equals the modulus of x is shown opposite. From the diagram, f prime 0 from the left is equal to minus 1. So basically the slope is minus 1, i.e. the slope of the curve to the left of 0 is minus 1. So it's going downhill, it's a negative curve. While f prime 0 positive, or from the right, is equal to positive 1. So the slope is going uphill. With a slope of 1 going uphill, it's a positive slope. I.e. the slope of the curve to the right of 0 is 1. It's positive, it's going uphill. As f prime 0 from the left is not equal to f prime 0 from the right, f of x equals the modulus of x is not differentiable at x is equal to 0, because minus 1 is not equal to 1. Note, one other term for the derivative dy dx is equal to f prime x is the differential coefficient. This is because we can write dy equals f prime x dx, and f prime x, the derivative, is the coefficient of the differential dx.